Hello everyone, my name is Matías Carendell. I'm doing my PhD at Universitat Politècnica de Catalunya at the Electronics Engineering Department, and I will be presenting my work, Contributions to the Pendulum Type Wave Energy Converter Systems for Oceanic Drifter Applications. The contents of my work are the following. I will start with the introduction, then I will talk about the Kinetic energy harvesting device, then I will present the power management unit, then the design of the real-time power monitoring drifter, and finally I will present some of the tests that we have been performing. So we all know the importance of monitoring the health of the ocean. Lagrangian drifters are one of the only units that helps us with that, as they are low-cost, low-power oceanographic autonomous device which passively follow the current while monitoring the sea parameters as current flow, temperature, salinity, or wave height and period. They are widely used in climate research, and one of the main challenges of these units is autonomy. As they may be deployed for more than 1 year, they need some natural source that provide energy to span their life. If we take a look at the commercial drifters, we see that it is very common to include solar panels at the drifter in order to expand their life. For example, Spoon Drifter is one of the commercial companies that excel fabricating drifters. They say that they can reach up to unlimited lifespan in propitious solar conditions. Nevertheless, solar solutions are not the most perfect way for drifters. Drifters should not be exposed to the wind, as we want information about the current. So if the drifter exposed to the wind, the motion data may be wrong. So if they should be mostly submerged, and then the irradiation at the solar panels may be attenuated. Also, we can find some fooling covering the drifter that may reduce deeply the radiation flow and the energy scavenged by the solar panels. That's why we started thinking in a kinetic solution. To do that, we started with experimental records and also using the simulation from OrcaFlex in order to see which is the main motions of the drifter in order to understand which is the motion that we should scavenge. The results say us that we have oscillation in the drifter in the order of, depending on the drifter shape, but it's normal found at between 1.5 and 2 Hz with this normal size and shape of the drifter. So we have a pitch and roll oscillation, and also we have a vertical vibration found at around 1 Hz. Also, we'll have the motion of the frequency of the wave, which is much more slow, so low frequency, but the predominant motion is the ones that I present. We developed several devices to scavenge this energy, as the electromagnetic solutions present at left and the piezoelectric found at right. I won't get into much detail of that. I will only say that they were not very competitive. So we changed into a pendulum type converter that turns the oscillation into rotation, and then using a micro electrical generator into electricity. It counts on a gear system to increase the speed and also a flywheel to accumulate this rotation. When we tested this prototype in a linear shaker, you can see how it converts the linear excitation into rotation, and then using the micro generator into voltage. Here I plotted the open circuit voltage of the generator, which is not present in the video. And you can see that it has AC and DC components as it oscillates with the frequency of the pendulum, but also have a DC component as it is all the time positive. The different parts of a kinetic energy harvester are shown in this figure. We first have the energy harvesting device, as I presented to you, the pendulum that we have developed. Then we need the core main unit of the system, which is the power management unit that has 3 main functions. The first one is to perform the maximum power point tracking to extract the maximum energy from the device. Then the storage control strategy to control the flow of the current between the energy storage element and the load, and finally to provide a fixed voltage supply to the electronics that we may have in the load. I've been working deeply in the MPPT techniques. As you can see, my device can be emulated, modeled by a Thevenin equivalent with a voltage source and a series resistor. And when I tested the device at different rotation speeds, I found that the power is completely symmetric. So the maximum power point is found at the half of the open circuit voltage. There are several ways of performing the MPPT. I will get into details, but we use the fractional open circuit one as it is a very low power technique. The thing is to open the circuits every time, sample the open circuit voltage, and then place the half of it in order to perform the MPPT. There are several commercial units on the market to do that, as a power management unit, from Analog Device, Texas Instruments, and also APs, which is a very new company. The problem with them is they are prepared for very slow sources as the solar panels, that they change very slow. We have a frequency in the order of 1 or 2 Hz, so we need to sample very fast to perform the MPPT. APs does that, so 3 times per second, which is not 16 seconds. That's very, very slow, but it's not enough. So we are working on speeding this MPPT with custom power management units. Then we have two main questions. So how do we monitor in real time the generated energy from the kinetic energy harvesting and the efficiency for the power management unit in the real test? And how do we emulate this C dynamics in a controlled test environment? Okay, to do that, the first thing, we designed a real-time power monitoring drifter where the kinetic energy harvesting system will be embedded, and then it will have different sensors to measure in real time the power in and the power out at the power management unit. And then it will have an Arduino-based microcontroller that acquires this data, and also through an inertial measurement unit, the acceleration and rotation of the drifter. And then it sends this data wirelessly to a computer, which can be in the boat, using Wi-Fi to load in real time what is happening inside of the drifter, the energy generated and how is it moving. We found several places to test this drifter that you can see here. We have the embedded kinetic energy harvester and the electronics of the device. We first tested, as I showed you, in the linear shaker to see in the first preliminary test. We also used OrcaFlex simulation tool to emulate how would be the dynamics of the drifter. This data of the motion of the drifter can be used to drive a robotic arm of KUKA to emulate the C conditions. We also used, and want to say thanks to people from UPC, the LIM wave-flume to emulate C conditions, and finally we performed a preliminary C test. I have a quick video that I want to show to you of the different parts of the test within the MELOA project, which is an European funded project. Here you see some of the OrcaFlex simulation performed at the beginning. Then using NX from Siemens, we designed the unit to scavenge energy from the sea, which is the double pendulum system. We tested, as I showed to you, in the linear shaker to see how is it turning the linear acceleration into rotation. And then we developed the system to acquire in real time using LabVIEW the data in the drifter test. This is the unit that do this test. Here you can see some images from the channel where we did some of the tests to see how many energy we are generated, changing the period and the height of the wave. Several units were developed. We also use KUKA arm robots using the data from OrcaFlex in order to see how the device is moving under different C conditions. Here you can see a real video of this test. And finally, we are doing preliminary real C experimental tests, and we have been performed some of them, but we are still on the loop. So next presentation, hopefully I will show you some of the results of this test. So I would like to thank you, Sarti and ECAT groups, the FA grant that I have from Generalitat de Catalunya, and also the MELOA funded project that has given me the opportunity of presenting that. And thank you to all of you for listening. Have a nice day.